Welcome to section 8.5. In this section we're going to be looking at the graphs of tangent, cotangent functions, cosecant and secant graphs. Before you start this section, you should have already completed textbook page 445, the exploration. So that means you should have already graphed a tangent function on your own before you start this. If you have not done that, then please stop and go back and complete textbook page 445. Okay, so first thing, we need to describe in our own words some of the important vocabulary terms, starting with asymptote. So I'm going to start with a picture. Some of the graphs that we've looked at, before we even look at the tangent graph, some of the previous ones that we looked at exponential functions, and they had an asymptote at the x-axis. That meant that our line could not touch or cross it. So an asymptote is like a boundary that a graph cannot touch or cross. Okay. Period we've discussed in the previous section. That is the horizontal length of one cycle. So this is going to be, so for example, we've been looking at sine functions. We know that one period is typically 2 pi. That's how far it takes for it to complete a single cycle. So we can think of period as the horizontal distance of a single cycle. One cycle. Amplitude, we talked about that before as well. That's the height from the midline to the local max or to the local min. So the amplitude is like the height. It's the height. X-intercept, that's just the point where your graph touches the x-axis. And you can say this however it makes sense to you. Touches the x-axis. Or the point where a function graph, the graph of a function or whatever, touches the x-axis. Transformations, these are like your vertical shifts, horizontal shifts, etc. Also, stretches and shrinks. A local max, I think of that as like a peak, and a local minimum, I think of it like a valley. So if I just look at my sine function or a cosine function, all of these will be considered local max. That's the local max. The valleys would be local min. Okay, so that's what that means. So the local maxima are your peaks, your local minima are your valleys. Alright, and then we're going to jump into some examples. Before we do our examples, you should have gotten a graph for your tangent function that looks like this. You should have found that your tangent function has period pi, and it goes, a complete cycle would go from negative pi over 2 to positive pi over 2. It's increasing. Okay. Has an x-intercept at 0, 0. And of course this is before any transformations take place. Alright, and then we also have a cotangent function. Alright, well remember, cotangent and tangent, they're reciprocals of one another. Okay, so how that translates on the graph is if you look at the tangent function and then you look at the cotangent function. The cotangent function, we're going to look at the period. It's going to have it's going to have a vertical asymptote on the x-axis. So we're going to look at it from the x-axis to pi over it also has period pi. So from 0 to pi is a complete cycle. Excuse me. This one is decreasing. But it does have period pi, just like tangent did. It's just that your vertical asymptotes are in a different place. Also, if you look at the graph of the tangent function, we had an x-intercept at 0. Alright, well, if you take the reciprocal of 0, you're going to end up with, like, let's say if you've got, anytime you've got an x-intercept on the original tangent graph, the reciprocal of that would put 0 in your denominator. So that means that the x-intercepts from the tangent function are going to become vertical asymptotes on the cotangent function. So that's why we're not looking at it from negative pi over 2 to positive pi over 2, but rather we're looking at it between the vertical asymptotes from the y-axis to pi over 2 to pi here. Okay? So the x-intercepts for the tangent function are going to be vertical asymptotes on your cotangent function. And then, let's try an example. Alright, so going over to, so you've got all these definitions that I've provided you with. We're going to look at an example. Let's look at number 1 on extra practice. G of x equals tan 2x. So a couple of things I need before I can do this. I need to determine my amplitude and the period. Alright, so for extra practice 1, my amplitude is the coefficient in front of the function, just like it was with the earlier functions we looked at. So because you don't see a coefficient, the amplitude is 1. And then we need to find the period. For the tangent functions, you determine the period by doing pi over the absolute value of b, because on these, one period is pi. So you're going to, and if you recall with the sine and cosine graphs, a period was 2 pi, so we did 2 pi over the absolute value of b. Now we're just going to do pi over the absolute value of b. So for this one, we'll have pi over the absolute value, our b is 2. So our period for this one is pi over 2. Okay? And now we're ready to graph it. So I'm going to draw, I'm hesitant to use this graph. I'm going to come over here and do my own. So alright, so looking at I'm going to go back and compare my original. This is the original tan graph. This is my tangent function. I know this tells me that I have a vertical asymptote at negative pi over 2b. And I have another vertical asymptote at positive pi over 2b. So let's find that. Where will our asymptotes be? So we're going to have an asymptote at negative pi over 2 times b, and we found b was 2. Yeah, b was 2. So negative pi over 4. So we'll have a vertical asymptote at negative pi over 4. So I'm just going to draw that asymptote in and label it negative pi over 4. And by symmetry, you'll have a positive asymptote at positive pi over 4. So you can go through the work, but it'll give you the same thing. So that's positive pi over 4. The tangent function, we know, is going to look like this blue curve between the two asymptotes. And it's going to cross through the origin. So we can draw that in. And then we can also put in some additional points. The halfway mark here, halfway between 0 and pi over 4 would be pi over 8. And then the halfway mark here would be negative pi over 8. And we're also going to have a point at our amplitude A. A is 1, so let's label that. Call that 1, 2, negative 1, negative 2. So at this halfway point, pi over 8, and up to the amplitude 1 will give us a point on the graph. and then we've got 0, 0, and we also have the point negative pi over 8, negative 1, which would be here. So those are 3 points on our graph, and that's all we need to show. So that's our answer. I don't know, did they ask us to do anything else on that question? Yes, so they want us to describe the graph of g as a transformation of the graph of its parent function. Okay, well this was the parent function. This was tangent. So parent just means that was the original. How does that compare? Well, it all comes, if you go back and look at your amplitude and b, we can find the number out front, just like these are the same rules that we used a long time ago when we were looking at absolute value functions and square root functions. A number multiplied to the front of your function, 1, would give you a vertical stretch or vertical shrink, but we didn't have that. But the 2 here, that's being multiplied to the x, is a horizontal shrink or stretch. With the horizontal ones, if you remember way back at the beginning of the school year, the horizontal ones you find multiplied by the x, and then you do the reciprocal. So this is going to have a horizontal shrink of 1/2. Okay, so the graph, let's see, the graph is a horizontal shrink of the parent function by a factor of 1/2. Okay. All right, so that's my answer for number 1. Okay. Let's look at number 2. Number 2 is a cotangent function. Okay, now you could go through and do the same work that you did in the exploration to obtain the graph of the cotangent function, but I am providing that graph to you. Okay, so this is the parent function, cotangent right here. We're going to use this to help us graph number 2, which is 2 times cotangent of 1/2 x. So let's start with the amplitude. Amplitude is going to be 2 because of that number. And the period is pi over the absolute value of b. So that's the absolute value of 1/2. So that's going to end up giving me a period of 2 pi. Alright, and then I'm going to go to my graph paper and draw that. Basically, I'm going to draw my parent function, but I'm just going to adjust the measurements to make it fit this one. Okay, so for number 2, we have g of x equals 2 times cotangent of 1/2 x. Period is pi, and I'm sorry, the period, we found the period to be 2 pi, excuse me. The amplitude we found to be 2. Now when I draw this one, if you look at the cotangent function, remember it's got a vertical asymptote at the y-axis. So when I draw this one, I don't really need the second quadrant. I'm just going to primarily focus on quadrants 1 and 4. Like this. So here's my y-axis. Okay. I need to find my vertical asymptote, so I'm going to have one at the y-axis. Where's the other one going to be? Well, if I look at my basic, I guess you could call it your cheat sheet, you're going to have a vertical asymptote at pi over b. Okay, so that means we have a vertical asymptote at pi over, got to asymptote, at pi over, and our b is 1/2, so that would be 2 pi, which makes sense. That's also the period, so that makes sense. So we're going to draw in our vertical asymptote at 2 pi. Okay, we want to find the halfway point here. The halfway point between 0 and 2 pi would be pi. And then we want to find the 1/4 mark, so that's going to be pi over 2. And then over here, this would be 3 pi over 2. Because it's going to be 1/4 of your period, half of your period, 3/4 of your period, and then that's the whole period. Okay, we're going to have, we know it's going to be shaped just like the parent function, so it's going to be coming down like this. We can find some points on here. We need to include our amplitude. We have amplitude of 2, so put that in. And we can find points on our graph by doing pi over 4b comma a. So that would be, for us, pi over 2, 1 is a point. And then we're going to have a point, our x-intercept will be at pi over 2b, which was pi. And then we're going to have a point over here at 3 pi over 2 down negative. And you know, I'm sorry, I messed up. My amplitude was 2. So this point should not be here, it should be up here, all the way up here 2. So pi over 2, 2. So sorry, I don't have any white out, so try to ignore that point. I'll put my finger on it. Alright, and then you're going to have a point at 3 pi over 2, negative 2. Down here. And now you can connect this with a curve. Like that. And then like this. Make sure it does not touch or cross your asymptotes. So that's what your graph looks like. And then they want us to describe, they ask us, describe the graph of g as a transformation of the graph of its parent function. Okay, so if we look at the equation, that's giving us a vertical stretch. So the graph of g, I'm drawing my graph so big I don't have space to write. The graph of g is a vertical stretch by a factor of 2, and the 1/2 here means that we have a horizontal stretch and you do the reciprocal, so a horizontal stretch of 2. By a factor of 2. Of the original parent function, of the parent function. Okay, so the graph of g is a vertical stretch by a factor of 2 and a horizontal stretch by a factor of 2 of the parent function. Okay, next. Let's look at I don't really feel a need to do 3 and 4. The only difference between 3 and 4 and the ones that we just did that I can see is that your amplitude is smaller than 1. So you just reflect that in your graph, and these are going to give you a vertical, because A is smaller than 1, this is going to be a vertical shrink by a factor of 1/4. That one's going to be a vertical shrink by a factor of 1/2. Otherwise, it's the same thing. So I'm going to let you think about those two, and then I'm going to go down to number 5. All right, number 5, we're given g of x equals 2 times secant 2x. So we got to talk about what a secant graph looks like. When you go to graph a secant or a cosecant graph, what you want to do is start by graphing its inverse, but do it with a pencil so you can erase it. Make sure you do it light enough that you can erase it. But we know that secant is 1 over cosine. Okay? We know that cosecant is 1 over sine. So what's going to happen with this, and I've also got this on your little cheat sheet that I printed for you. What's going to happen with these, if you look at this, secant is 1 over cosine. If you look at the gray on your paper, this gray is cosine x. Secant is going to be, it's going to have vertical asymptotes every time cosine has an x-intercept. So you've got an x-intercept. So your original cosine function has an x-intercept at negative pi over 2. It has one at positive pi over 2. Every time it has an x-intercept, because it's the reciprocal, that puts 0 in your denominator and creates a vertical asymptote for the secant function. So you'll have vertical asymptotes at negative pi over 2, positive pi over 2. But all you're doing though is like the peaks and the valleys from the cosine function are going to touch your secant graphs. And then you're just going to draw them like upside down U's. So you'll have U's pointing down and U's pointing up every time you have a peak or a valley on cosine. Okay, so if you see that relationship, then it shouldn't be too difficult to graph one like this. The period is going to be the same as cosine. It's also 2 pi. But you're going to want to focus on it between the asymptotes, the vertical asymptotes. And then if you look at the cosecant function, it's the same thing. It's the reciprocal of the original sine function. So the original sine function's in gray. Every time sine has an x-intercept, you're going to have a vertical asymptote on the cosecant function. And you're just going to have them touching at the peaks and the valleys, but they're going to be like flipped upside down in between the asymptotes. Okay, so we're going to use that to help us with this one. We're going to do 2 times secant 2x. So my amplitude is 2. The period, now be careful when you get here. Okay, remember secant has the same period as cosine, and cosine had a period of 2 pi. So you're going to do 2 pi over the absolute value of b. So that's just going to be, for this one, it's just going to be pi. So this one has period pi. And if you want, before you even graph it, you can talk about the transformations. This 2 is a vertical stretch by a factor of 2. And it's a horizontal shrink by a factor of the reciprocal of this of b, so 1/2, by a factor of 1/2. Okay? And that's all we need to graph it. So I'm going to start by, I'm going to lightly sketch the cosine graph first with the same I can't think of the right word. I'm very tired right now. Alright, so cosine, I want an amplitude of 2. So there's 2 and 1. Yeah, negative 1, negative 2. And then I would have the cosine function has period, it's got period 2 pi. So we'll put 2 pi here. And then this is going to be pi. And then that's pi over 4. 3 pi over 4. So what does the cosine function look like? Cosine, remember, would start at the very top. And it would go like this. Come all the way down. It would have an x-intercept here. And it would go all the way back up to the peak. Okay? And then I can continue the pattern over here as well. So it would go back through like this and all the way down like that. Every place that cosine touches the x-axis, creates a vertical asymptote for secant. So all of these x-intercepts become vertical asymptotes. And I should not have drawn this one in over here because that was for the cosine function. It does not necessarily apply to the secant graph. Okay, but then once you've got all this information in, it's easy to draw the graph that you need. Your graph is going to basically touch at the peak, and I'm going to have to kind of superimpose it, but it's going to be between the asymptotes. It's going to come down like this. And then over here, this one's going to come, it's going to share this point at the valley of the original cosine, but then it goes the opposite direction. And that's it. That's one period of 2 secant 2x. So that's what your graph would look like there. Again, it would probably be difficult to draw that on the graph that they've given you there. Alright. So I think you're good. I think you can do these. You should be able to handle it. Number 6 is going to be cosecant. It's going to be the 1 over sine function. See what you can do with that. Let me know if you need help. And that is it for section 8.5. Thank you.